In this video, I want to show an example of computing some values of binomial coefficients and using that to discover some extra properties that binomial coefficients have. Again, I really recommend that you do this yourself before you watch this video. So if you haven't done that yet, pause it now and see if you can fill in a little table like this for certain values of n and k. What values do you get for these and what patterns do you notice? So let's start filling this in. So first of all, when n and k are both 0, right, I should get 1. So actually we saw in the previous video, anything choose 0 is going to be 0. If I have 0 things and I want to choose nothing, there's one way for me to do that, which is to do nothing. Okay, so this should be 1. Makes sense? What about here? What about when n is 0 and k is 1? So this formula doesn't actually really make sense in that context, because 0 minus 1, here I get a negative 1 factorial. Okay, and I don't know what negative numbers factorial means. Combinatorially, this really should be 0, because if I have 0 things, I can't possibly choose one thing out of the 0 things that I have. So we're going to say this is 0. And really we should amend the definition slightly to say, when n is 0, so this is when n is greater than or equal to 0, and 0, k is between 0 and n, right? So if I have a negative number of things, it doesn't really make sense. If I have, I can't choose a negative number of things. So if k is negative, I can't choose a negative number of things. And also if k is bigger than n, I can't choose more things than I have. So in any other cases, we're just going to say this is 0. So 0 otherwise. Okay. So these are all going to be 0, right? 0, 0, 0. And I'm not, in general, going to fill in all the zeros. So basically, we're going to end up with sort of this triangle up here. These are all the values where k is bigger than n, and those are all going to be 0. Okay, so let's focus on filling in the ones down here. So when n is 1, if k is 0, I get 1. And if k is 1, I also get 1. Okay. When n is 2, I should have, well, again, these are all 1s, right? So we saw in the last video that anything choose 0 is going to be 1. I have one way to choose nothing. Okay. How about here? So n is 2 and k is 1. So we could say either just think about how many different ways do I have to choose one thing out of 2? Well, there's 2 ways. I can choose this thing or I can choose that thing. You can also put the numbers into this formula and see that you get 2. Right? So this is 2 factorial is 2. This is 1 factorial, and this is also 1 factorial. So I just get 2 divided by 1. Okay, and then this is again 1. So picking 2 things out of 2 things, there's just one way to do that. I pick both. Okay. Let's see. When n is 3, so another thing we can see is that actually, when n is 3 and I'm picking one thing out of 3, I can choose the first thing, or I can choose the second thing, or I can choose the third thing. I have 3 ways to do that. In general, combinatorially, it seems that if I do n choose 1, I should always get n. There should be n ways I can choose any one of the n things. And indeed, if we look at the formula, we see that works, right? So when k is 1, here I get n minus 1 factorial, and that cancels out with almost all the things up there except for the n. So here's another property we've discovered. So n choose 1 is equal to n. That's generally true. So I can fill in the rest of this column here, 4, 5, 6. Okay. How about choosing 2 things out of 3? So let's do over here. So 3 choose 2. And here's, I didn't say about how to actually go about computing this, but right, so it should be 3 factorial divided by 2 factorial times 3 minus 2 factorial. And rather than just computing out this number and computing these numbers and multiplying and dividing, there's a lot of canceling we can do. So when you're computing these by hand, you want to cancel as much stuff as you can before you actually do any multiplication or division. So this is going to be 3 times 2 times 1 over 2 times 1, and here I have, this is 2 times, no, that's just 1. 3 minus 2 is 1. Okay, so I can cancel the 2's, the 1's I don't care about, and so I'm just left with this 3. And we really should have known that, actually, because of symmetry, choosing 2 things out of 3 is the same as choosing the 1 thing that I don't choose. And so this has to be equal to what we already got for 3 choose 1. Okay, so this is again going to be 3, and then we know that 3 choose 3 is going to be 1. Okay, let's do another example here, filling this in. So 4 choose 2 is going to be 4 factorial. I won't bother putting the 1 this time. And then I get 2 factorial in the bottom, which is just 2, and then I get another 2. So this is 2 factorial, and then 4 minus 2 factorial. I can do some canceling. Why don't we just say both these 2's will cancel with the 4, and so this is 6. So I get a 6 here, and then by symmetry I should get a 4 here, and then a 1 here. And let's see. We'll do one more example. 5 choose 2. So we get 5 times 4 times 3 times 2 over, I get 2 factorial, and then 5 minus 2 factorial is 3 factorial. And I can cancel a bunch of things. The 2 cancels with the 4, leaving 2 up here. And so I just, in the top I have 5 times 2, and I'm going to get 10. Right? Incidentally, everything in the bottom is always going to cancel out. You're only going to be left with things on the top. Why is that? Why do we know that? Well, because, remember, we got this formula by counting things. This formula gives us the number of ways to do something, and so it's always going to be an integer. It has to be, because we're counting. And so we're never going to get a fraction where we've got, something in the bottom that doesn't cancel. So that's 10. So I'm not going to actually compute the rest on the board. You can do that for yourself if you want. I'm just going to fill in the rest of the table. Okay, so this is going to be 10, 5, and 1, and then down here we're going to have 15, 20, 15, 6, and 1. And you can keep going further if you want. So that probably looks familiar to you. This is in fact Pascal's triangle. And I think this video is long enough, so I'm going to stop, and but in another video we'll look at some of the patterns that we see and see if we can connect those back to binomial coefficients and think about what those patterns mean in a combinatorial sense.